In this video, we are going to consider the region bounded by the graph of y equals x times x minus 1 squared in the x-axis. And we're going to revolve that region about a few different axes. But let me start by drawing the graph of that region. So if you remember some information about graphing polynomials from pre-calculus, you might remember that the zeros of this polynomial are the x-intercepts of the graph. So the zeros of this polynomial would be x equals 0 and x equals 1 from the two factors here. So that graph will have x-intercepts at 0 and at 1, which I'm going to put way over here. Okay. Also, notice that the degree of this polynomial is 3, and it's got a positive leading coefficient. So if you remember that information about end behavior of the graph of a polynomial function, when it has, so this will have odd degree because it's degree 3. If you multiply this all out, your leading term will be positive x cubed with a, like I said, positive leading coefficient. So when you zoom way out, the graph will look like the graph of a y equals x cubed graph. So the end behavior is it's going to go down on the left and up on the right. Now to fill in the middle part of the graph, you can use multiplicity. So the fact that the x equals 0 factor here, so just x, has multiplicity 1. So odd multiplicity means the graph goes through the x-axis, and even multiplicity, like you have at 1 here, it's to an even power, tells you that the graph will touch the x-axis and turn around. So just quick pre-cal review there. I'd take the opportunity. So we're looking at the region bounded by this graph and the x-axis. So the enclosed region is this region here. So we're taking that region now and revolving it about, so first the y-axis, so we're revolving it here. Now, first thing to decide would be how should we draw the rectangles? How should we slice this region? Notice that if we slice it horizontally, so if we draw our rectangles going horizontally like this, one issue is that both ends of that rectangle lie on the same graph, lie on the graph of this y equals x times x minus 1 squared. Also, when you use a horizontal rectangle, remember that means that you're integrating in terms of y, because you're taking your partition along the y-axis here, which means we need to take our boundary equations and solve them for x, and have this boundary written as x equals something, have this boundary written as x equals something. Well, solving this equation for x is not a trivial exercise. So that's something that would take a lot of effort. That's not needed. So here's a case where just going by the setup of this region, it makes more sense to use a vertical rectangle. So I'm going to have the typical rectangle set up vertically, which means it's important to note right away, so the width of the rectangle here is dx. So we're going to have an integral in terms of x. Now, notice also that the rectangle is parallel to the axis of revolution. So when you revolve this rectangle, it's going to form this empty tube sort of shape, which we refer to as a shell. So because the rectangle is parallel to the axis of revolution, we know that we need to use the shell method, and we know that it's going to be an integral written in terms of x because we're using a vertical rectangle. So two very important things to note. Formula for the shell method, which was explained in the notes, is 2 pi times the integral from a to b of the radius times the height times the thickness of the rectangle, which is dx, or the thickness of the shell. Okay, so there's our formula. So in this case, A, when it's revolved about the y-axis, we need to find the radius and the height of this shell. So for the radius of the shell, that's going to be the distance. Well, here, it's this distance here. This would be the radius of the shell, if you can kind of see that from my drawing here. This is r. Now, when you set up integrals with the shell method, you need to label the position of your rectangle using the variable of integration. So in this case, x. It's an integral in terms of x. Call the position of your rectangle x. Now, our volume integral is going to be 2 pi integral as x goes from 0 to 1, because those are the lowest and highest x values corresponding to this region. At any point along that integration, we call the position of the rectangle x. So remember that these integrals represent an infinite sum. They represent the Riemann sum. So like I said, it makes my picture look really cluttered, but I mean, imagine you have all these rectangles. And so we're calling the position of the rectangle x, and maybe picture x sliding through the region as we take that infinite sum. So if we call this position here x, we're revolving about the y-axis, which is x equals 0. Then the distance between those, if you can see that, would be x minus 0. This radius here, in this case, for the shell method, is just x. Or that's what in Mr. Stockton's videos he refers to it as average radius. So again, it's because the position of the rectangle is set up as x, since that's our variable of integration, and we're finding the distance to the y-axis, which you can think of as x equals 0. So it's x minus 0, so it's just x for the radius. For the height of the rectangle, I want to get another color. That is this dimension here is the height. So we do top minus bottom to determine the height of the rectangle. The height will be, so the boundary along the top is this curve. Along the top we have the x times x minus 1 squared curve. Along the bottom here we have the x-axis, which is y equals 0. So the height is just x times x minus 1 squared. If you want, I could write a minus 0 here if you want to look at it as top minus bottom. But so the height in this case is x times x minus 1 squared. And then dx. So yeah, we can multiply this, right? This is x squared. You could multiply out, if you were going to evaluate this, you would multiply out the x minus 1 squared and so on. In the homework, I'm okay with it if you leave it like this. So there's your answer to part A. Okay, so what if it's revolved about the line x equals 3? So again, I've cluttered my picture. I'm going to have to draw a fresh picture. I tend to write all over my graph while I answer these. So here's the answer to A. I'm going to get rid of that as well, since you guys can pause. I wish I should have kept that shell method formula. Oh well. So what if it's revolved about the line x equals 3? Okay, so let's think about that. So now we know this graph has intercepts at 0 and 1. Let's say 3 is over here. I know my spacing isn't equal, but maybe you can, well, okay. Now I feel guilty about it since there's 1, 2, 3. Okay, graph of, let me draw it in blue this time, of that polynomial function looks like this. And then the other boundary is x equals 0. So the enclosed region is this region here. We're going to use a vertical rectangle because that's the best way to slice this region. And now it's revolved about the line x equals 3 over here. So still, the rectangle is parallel to the axis of revolution. So it's still going to be shell method whenever your rectangle is parallel. If I revolve this rectangle, I'm going to get this really wide, in this case, open tube sort of shape. So shell method volume equals 2 pi integral from, we're still integrating from 0 to 1. This region just corresponds to x values between 0 and 1. And so when you set up those limits of integration, imagine you're allowing this rectangle to slide through the region. And with each position of the rectangle, which we're going to call the position of the rectangle x, with each position between 0 and 1, you're taking that rectangle, revolving it about the line x equals 3 and forming this shell. And then you scooch it over a bit, revolve that rectangle, form another shell. And then the idea is we're adding up the volumes of all of those tubes. Okay, so integral from 0 to 1 of the radius times the height times the thickness. So in this case, 0 to 1, what's the radius? Radius is the tricky part too. I mean, radius is always a simple expression, but it's the part that students have the most trouble with. So let me get rid of a little bit of this. So we're calling the position of the rectangle x. When you revolve this rectangle about this line here, the radius will be this distance here. Or again, this is what Mr. Stockton refers to as average radius. Now, so to find this horizontal distance, do right minus left. So the axis of revolution on the right here is x equals 3. We're calling the position of the rectangle over here x, and so the radius is 3 minus x, right minus left. There. The height of the rectangle is the same height that I discussed in the previous, when we revolved about the y-axis. So the height, you do top minus bottom. So the top boundary is the y equals x times x minus 1 squared boundary. And then on the bottom, it's just y equals 0. So minus 0, which you don't really need to write. So the height here is x times x minus 1 squared dx. Okay, and then there's your answer to part B. Now, I'm just making sure it's all on the screen. Okay, so now revolved about x equals negative 2. One last time here. And again, I mean, I clutter up my pictures so much that I need to draw a new one every time. Okay, so negative 2. So that's back here. So the boundaries, so just the region is this hump here. Here's a typical rectangle. Again, it's parallel to the axis of revolution. So that's what tells us it's a shell method, so I'm still using this formula. And the limits of integration stay the same. You shouldn't be changing your limits of integration just by changing the axis of revolution. That shouldn't happen. The limits of integration are determined by where the region is. So the region lies where x is between 0 and 1. So we're only integrating from 0 to 1. You're not integrating over here. We're not putting any rectangles to revolve over here. We're only setting up the rectangles between 0 and 1. If you're using a shell method, call the position of your rectangle x, or y. If it was horizontal, we would call it y. Because if you're sliding horizontal rectangles, then y is what gives you the position of the rectangle. Whereas if we're sliding vertical rectangles, x gives you the position of the rectangle. So the radius here is the distance from the rectangle to the axis of revolution. So the radius now is this. Because, I mean, if you imagine that you revolve this rectangle, I mean, here's your tube. The radius of the tube will be this distance here. So do right minus left. So we've got x here. We've got x equals negative 2 here. So x minus negative 2. So x plus 2. Which x plus 2 makes sense because x is the distance from the y-axis plus 2 units of empty space here. So x plus 2 for the radius. And then let me fill in some of the rest of this. Okay, so now we need the height. The height is the same again. Top minus bottom. Y equals x times x minus 1 squared. Down here, y equals 0. So the distance between those is x times x minus 1 squared, just like it was in the previous two examples. X times x minus 1 squared. And again, you can leave it here. If I was demanding that you integrate it and find the actual volume, you would have to multiply all this out. So you would want to square x minus 1 first, and then x times x plus 2, multiply all that out, and then it would just be power rule for integrating.